It's like so fun to talk about this stuff with you guys. Okay. Let's suppose now we have a vector. Let's go to the math. And it's not linear. Up to this time, you've worked with things where that's going to be a matrix. But this time it's not. Well, you could find the multidimensional version of a tangent line. And the way we've been using that in this class is the linear part is a matrix. So you can say x prime is equal to ax plus some leftover stuff, like a Taylor series, right? If you have a Taylor series expansion, you take the first thing would be the linear thing, and then the stuff after it would be the stuff that you might drop off. And instead of considering this stuff here, you're just going to drop it off and look at this, which you have the tools for looking at. You already know how to do, like, find this matrix, find the eigenvalues. If the eigenvalues have negative real part, the equilibrium is stable. If the eigenvalues have anything other than that, you don't have stability, right? You might have a saddle. You might have it's completely unstable, so they're moving away. So you did all that with Dr. Gross, right? Okay. It's not so cut and dry when you have this for a nonlinear equation, because you could have what was just happening in that Lorenz attractor. You only know the behavior close by that equilibrium point. And you could see it wasn't going into that equilibrium point because it's unstable, moving away. But you couldn't say far away from that what was happening. So you only know what's happening local to that equilibrium point. So this section is 9.3. It's called local stability. That's why it's not global stability. I can't tell you what's happening everywhere, but I'm going to tell you that if your trajectory comes close to this equilibrium point, it's going to be unstable. That's I can tell you. All right, so example step by step. With Lorenz. So your book takes some pretty easy things. They don't have parameters in it. Most of our stuff does have parameters in it, and it walks you through it with some toy examples. If you want to see that, go ahead and see that. They do the theory. They're not explaining it the way I did, where I'm like talking about it like a Taylor series dropping off, but that is what you're doing. They talk about perturbations to linear parts. So they talk about this being a perturbation to the linear part. But the reality is it's the higher terms in a multidimensional Taylor series. I'm just going to throw them out and say, pretend they're not there. The book's examples are very good. The book is really good. So and it's not hard to read. You can actually look at it and go, oh, I get this. Okay, so here's what the example looks like. Looks super easy. Dx dt is equal to sigma times y minus x. This one's linear. dy dt is equal to x times rho minus z minus y, and dz dt is equal to x, y minus beta z. That's the Lorenz model. Step one, you'll want to take this down because I didn't write this into the in-class assignment. Find the equilibrium. There is probably going to be more than one because it's nonlinear. So you might have all kinds of weird things happening. And indeed you do. You have x equals 0, y equals 0, z equals 0. And then Mathematica gave me, so I did Mathematica, and it gave me another one. But I think these are plus and minus, so it only gave me one. and Z is equal to rho minus. A little bit abstract algebra. You always have conjugates, so things come in pairs, kind of from the quadratic formula. You see that. And rho in this case has to be bigger than 1. It doesn't have to be, but typically we have it bigger than 1. I'm actually going to erase this because I'm going to stick in rows that are not bigger than 1. All right, good? So in JEDI, I know you do Jacobians. In 255, you definitely do Jacobians. That material is just flying by. When I taught it, it's like I couldn't breathe. And I couldn't explain anything. I was like, just open wide. We have another method today. But just recall the word Jacobian. What you probably didn't get in that class is the Jacobian is the multidimensional version of a first derivative. That's what it is. So step 2 is to find the Jacobian. Do you remember this word, Jacobian? So I did this by hand. I didn't go to Mathematica and do it. And I cross-checked myself a million times because when I do things by hand, one of the reasons I picked up Mathematica, there's new software. Typically, you're going to get that from your faculty professors. Not me. When I saw Mathematica, I was like, this will do algebra for me? I'm taking it. So back then, it was different. It was not something that required in a class. It was a tool that I could just pull to do work, research. It's like if there was something that was going to do the algebra for me, I was going to pick it up. So I didn't do this on algebra. I did it by hand, just looking, and I cross-checked that I got my partial derivatives right. That's what you get. Doesn't look bad for a matrix. That's why I was kind of shocked. I don't think I've ever done this before, actually, with the Lorenz model. So step 3, plug in an equilibrium. Well, I started easy first. Started with 0, 0, 0, and I plugged it into the Jacobian, and I got minus sigma, sigma 0, rho minus 1, 0, and 0, 0, Still doesn't look bad. You've seen worse. You've probably seen worse this semester in linear algebra. Oh, but when you try to find the eigenvalues, it's bad. Okay, good. If you have linear algebra, you can take that one to your linear algebra class and say, can we analyze this matrix? Because it turns out to be a nightmare. But then I'm already on page 3. Like, I committed already. We're gonna go take this to the end. So step 4, define the eigenvalues. And it turns out Mathematica gave me minus beta, and lambda 2 is 1/2 times a holy mess This is a 2, not a Greek letter. And lambda 3 is the conjugate of that. Let's do this. Can I do 2, 3 so you don't have to write it again? Plus and minus. Do that. Well, how the heck am I supposed to tell what the sign of this and if it's got a negative real part? Like, there's like so many letters in here, I can't just look at it. So I went to Mathematica and I plotted it to see if it's negative. And I'll show you what that looks like. I'll show you in a second what that looks like. So I plot it as a surface. So you did plot 3D in your Jedi math class. I know you did. I know you're blocking it out, but you did it. So what it looked like was a surface that was like a weird looking folded plane kind of thing, and it looked like it was over. I just took the discriminant and I asked, is this ever negative? It turns out it actually is, but the way the graph is made, you know, Mathematica chooses the axis so it looks good. It looked like it didn't dip below the floor, but it does, just a wee bit. So there is a section where this actually does become negative, but this is positive, and then I graphed the whole thing to see if it's a positive surface, and it turns out it is, except in this region where I didn't see it from Mathematica. But for the most part, it turns out that this is always negative. This overwhelms this guy, and this is negative. So what do I know about the eigenvalues? They're all negative. What does it tell me about the solution? Asymptotic, but we have to say locally. We got to cover our butts. So step 5, make a conclusion. I'm going to say almost always. Locally, asymptotically stable. In the region where it's not locally asymptotically stable, that I didn't see, I'll show you what those look like. I just couldn't see it. So this is the failings of using something like Mathematica and just making a knee-jerk response to the whole thing. It turns out that the other two take over. The other two equilibrium values take over. Go ahead.
It's probably also pretty difficult to have a guaranteed answer with the Lorenz equation.
It actually, you mean like what we call a closed form solution? Like you can actually write down x of t is this and y of t is that what you're looking for? Absolutely not. You cannot. But most of these equations, it used to be in the old days that we just learned how to write solutions down. That was my differential equations class. I did tons and tons of grinding out solutions to things. And then somebody told me one day, hey, most of the interesting things in life you can't solve. I'm like, why did I spend a whole class with stuff that is like nobody cares about? Because by the time Mathematica came, it could do all that for you. But this is an interesting model. And so, no, you can't write down anything really interesting. You can't write down the solution. But a lot of people have been interested in this model. They're excited by it as I am. So there's tons of analysis that's been done on these models. And so you can find all that on the internet. Students have done it as a capstone project. They've written it all out. It's available online. People have taken it as a master's thesis to redevelop this expository master's thesis. So you can find really well-written stuff about Lorenz equations. All right, so I'm actually going to show you. Okay, so they're locally asymptotically stable for the most part.
Are parentheses applying to the whole thing?
Yes.
The 1/2?
Yes. We do this all the time in real analysis. Let 1/2 be 1. It actually doesn't matter, right? So we set pi to be 1 all the time. So really, all you care about is the sign of this thing. All right. So one more thing. because you have more eigenvalues, you have to do the same work again. So you're going to rinse and repeat everything for step 3, for step 3 above. Rinse and repeat. And I went and I'm going to actually show you what it looks like, but then we're going to go to actually numerical simulations so you can see. And I'll tell you what the math says. You can't just do it by hand. Even Mathematica is going to fail you here. Like Mathematica was my friend until I tried to put in the second equilibrium. Then it said, no, I'm out. I'm going to bed. Not going to help you anymore. So I'm just going to put equilibria. Let me put lambda 3. Let me put the non-zero equilibrium, the first one. You get this guy. And now you get some messier looking stuff. And where it started trashing me and leaving me behind was when I asked it to find the eigenvalues of this thing. It gave me this weird output. And then I went and looked online, like, what does this weird output mean? And it started talking about complex analysis. And it gave up on me. It just quit. This is the matrix you get. So, step 4, to find the eigenvalues. Mathematica shut down. I went into some of these master theses. It turns out that you have to analytically look at those eigenvalues for the signs using something called the Routh-Horowitz criteria, which is beyond this class. So you can't just numerically look at it anymore. But so step 3, step 4 is to find the eigenvalues. It's a nightmare. Like you wake up in the middle of the night and go, what were you dreaming about? The eigenvalues at the other equilibrium for the Lorenz attractor. It's that bad. So like, you've done it in Jedi math, you've done something in Mathematica and just spit out stuff with number symbols in it and some weird stuff. And you're like, what does this mean? And then you start trying to track down what it means. And like, it tells you it's really complicated. So that's basically where we're at. Okay, so what I can tell you is going online and looking at the signs of these things, it turns out step 5, what you can say, you have a theorem. Called Routh-Horowitz. When I was graduating with my degree, I graduated with a dynamical systems degree, and it just basically meant you're a mutt. You don't have any specialization in any kind of math. Routh-Horowitz comes from complex analysis. It's another area of math. So you just had to pull from other areas of math the theorem that you needed to, and you had to understand it to apply it to this thing. But it's beyond our class. I'm not going to cover it. But what you have is that if sigma is bigger than rho plus, or sigmas are bigger than, beta plus 1. Is it rho plus 1 or beta? It's rho. And this weird condition that rho is less than sigma times sigma plus beta is 3, and sigma, and I'll just tell you these things come from this criterion, so it's like it's not easy to get this. You get so that other equilibrium 0, 0, 0, when it exists, the other two don't, because you have they don't exist. They only come into view if this criteria is satisfied. So we call that a bifurcation. So they suddenly appear, and then you get this number. This number here is called rho H. So it's like a threshold. And if rho is less than or equal to rho H, 0, 0, 0 stable, and no attractor. You don't have that cool thing I showed you at the beginning. If rho is bigger than rho H, get the butterfly. And that's why people pick this up as a master's thesis, even though he published this stuff in like 1963. Not easy. And you learn a whole lot. I actually think it would be a cruel capstone if I gave that to someone as a capstone to do. It's like you spend all your time grinding through inequalities and figuring things out and reading theorems that from complex analysis just to figure out the stability of these equilibria. So